Welcome to Physics Topic 1B, where we delve into the concepts of energy, covering gravitational potential energy, kinetic energy, work, and power. Let's begin with an introduction to how energy provides an alternative perspective on motion. Welcome back. Having discussed motion, we now turn to an alternative view, energy. We'll follow how objects affected by gravity change their energy stores, applying Newton's laws to everyday situations like falling objects or a soccer ball's flight. Our first core concept is gravitational potential energy, or EGRAV. Gravitational potential energy is the energy an object possesses due to its position in a gravitational field. Near Earth, we calculate the change in GPE as mass times gravitational field strength, usually 9.81 newtons per kilogram times the change in height. For instance, a 2.2 kilogram brick lifted 1.24 meters gains 26.8 joules of energy. Next, let's explore kinetic energy, the energy of movement. Kinetic energy is the energy of movement. It depends on the square of the velocity, so doubling speed quadruples the energy. Take a 400,000 kilogram jet cruising at 250 meters per second. Its kinetic energy is a massive 12.5 gigajoules. Always remember to convert units to SI, like kilometers per hour to meters per second, before calculating. We now turn to one of the most fundamental principles in physics, the conservation of energy. The principle of conservation of energy states energy cannot be created or destroyed. As an object falls, GPE is transferred to kinetic energy. If we ignore air resistance, the mass cancels out, confirming Galileo's idea that all objects fall at the same rate. V equals the square root of 2 grams times delta H. Let's apply this. If you dropped a coin from the top of the 830-meter-tall Burj Khalifa, it would hit the ground at 128 meters per second, assuming no air resistance. Designers use these same equations to determine how high water must be ejected to reach a certain height. Next, let's understand the concept of work done in physics. Work is done when a force causes a transfer of energy. When a force acts at an angle to the direction of motion, we only use the component of the force in that direction. Our general formula becomes work equals force times displacement times the cosine of the angle between them. Finally, we cover power and the critical concept of efficiency. Power is the rate of energy transfer. 1 watt is 1 joule per second. We often deal with large scales, using kilowatts up to terawatts. For example, a forklift lifting a 120 kilogram crate 5 meters in 4 seconds exerts 1.47 kilowatts of power. No machine is perfectly efficient. Some energy is always wasted, often as heat. We calculate efficiency by dividing useful output by total input. If our forklift uses 3,000 joules of electrical energy to do 1,470 joules of work, it is 49% efficient. Let's summarize these concepts with some applications and practical skills. In the lab, we can determine G by measuring the velocity of a falling object from different heights. Plotting versus squared against delta H gives a straight line where the gradient equals 2 grams. This graphical analysis reduces the impact of random experimental error. We can apply these concepts to sports. When a player kicks a ball, they do work on it to provide kinetic energy. By knowing the force and the time of contact, we can calculate the ball's final velocity, often over 44 meters per second, and even estimate the force a goalkeeper must exert to stop it. Master these formulas and their SI units, and good luck with your practice.